Did you know that the Brooklyn Bridge has stood strong for more than a century thanks to 14,000 miles of steel cables? So what in the manufacturing process allows these strands of steel to carry such colossal structures? To create a cable that is strong, resilient, and reliable enough for life or death missions, the journey begins in iron ore mines and continues inside the steel mill. There, alloys are melted at blistering temperatures, cast into billets, and subjected to rigorous inspections before being drawn into wires and twisted into the finished cables, ready to serve projects around the world. This video will take you through that entire process, from technical details to massive machines to intricate operations, to explain why something that looks like nothing more than twisted steel can endure for decades in the harshest conditions. History of steel cable. Steel wire rope was born in the 1830s in the deep mines of Germany, when hemp ropes could no longer handle the loads. By replacing the old material, mine hoist could descend hundreds of meters underground more safely, opening the way for large-scale industrial mining. Nearly 2 centuries later, this material has spread across every field. Each year, the world consumes more than 10 million tons of steel cable, found in infrastructure, heavy industry, oil and gas, shipping, and even renewable energy. Millions of elevators around the globe rely on it, allowing skyscrapers to rise and shaping the skyline of modern cities. What's truly astonishing lies in its ratio between its small diameter and enormous load-bearing capacity. Bundles of tightly twisted steel wires not only provide flexibility, but also distribute force evenly across their cross-section. As a result, a cable only a few centimeters thick can support hundreds of tons, a mechanical marvel of the modern world. Raw material extraction. The journey of steel cable begins in massive ore mines, deep underground. First, high-powered drilling systems bore into solid rock to make holes for explosives. Controlled blasts fracture the rock, releasing blocks of reddish-brown iron ore. Then, enormous hydraulic excavators lift boulders weighing dozens of tons and load them onto mine trucks with payloads of hundreds of tons. These trucks move continuously along dedicated routes to carry the ore out of the pit. At the stockpile area, the ore is dumped into hoppers and transferred onto conveyors stretching for hundreds of meters. There, vibrating screens and magnetic separators remove dirt, sand, and other coarse impurities. The pre-processed ore is often crushed to smaller sizes to make it easier for transport and smelting. Later, specialized rail wagons and bulk cargo ships then take over, each hauling thousands of tons at a time. This entire cycle of extraction and initial processing runs without pause, ensuring a steady supply for the steel industry and guaranteeing enough raw material for cable production. Steel cable manufacturing process. When the ore trains arrive at the steelworks, the smelting process begins. Thousands of tons of iron ore, mixed with recycled scrap metal, are fed into an enormous electric arc furnace as tall as a multi-story building. Inside, giant graphite electrodes channel immense currents, generating heat that exceeds 2,900 degrees, hot enough to melt solid metal into a swirling mass that glows like volcanic lava. To give the steel its desired mechanical properties, engineers carefully add manganese to increase strength, chromium or nickel for corrosion resistance, and silicon to enhance ductility. At the same time, quicklime and fluorspar are introduced, forming a layer of slag that rises to the surface, acting like a natural filter. This slag absorbs impurities and refines the molten metal, leaving the steel cleaner and stronger. The entire mixture is stirred continuously by massive electrodes, while modern sensors monitor the chemical balance with precision,
ensuring that every batch of steel meets exacting standards. Once the molten steel has been refined, reaching the required purity and chemical composition, it moves on to the casting stage. Unlike the old days of pouring batch by batch, today, the hot steel is cast continuously into copper molds equipped with forced water cooling systems, As the liquid metal touches the cold mold walls, the outer shell solidifies instantly while the core remains molten. Solidification then progresses from the outside inward, forming solid billets several meters long, typically with a square or rectangular cross-section. Immediately after leaving the mold, the billets are still at thousands of degrees and are sent directly to the primary rolling mill to take advantage of the retained heat. Here, massive alloy steel rollers, each up to several meters in diameter, rotate continuously, applying immense pressure on the billet. With each pass between the rollers, the billet is flattened and elongated, its thickness reduced while its length increases. This process repeats across multiple rolling stands, gradually transforming the billet from a square or rectangular section into smaller semi-finished shapes, such as round bars, flat strips, or long slabs. The high temperature keeps the steel ductile, allowing it to deform without cracking. At the same time, the repeated mechanical forces realign the internal grain structure, making the steel more uniform, stronger, and more stable before it enters the wire drawing stage. After being hot-rolled into semi-finished products, the steel is sent to the cold rolling line to be drawn into smaller wires with precise dimensions. The process begins as the glowing hot bars from the rolling mill are cooled using a high-pressure water spray system. Next, the steel passes through a series of rolling stands. Each stand contains a large alloy rollers that apply massive pressure, gradually thinning and elongating the bar. With each pass, the cross-section of the steel, whether square or rectangular, is reduced and reshaped into round or flat forms suitable for wire drawing. Once in the wire drawing stage, the steel passes through a succession of dies with progressively smaller diameters. Each pass makes the wire thinner, the surface smoother, and the internal structure more uniform. This stage is carried out at room temperature, but requires strict control over pulling force, speed, and the friction between steel and die. Even the slightest deviation can cause the wire to break, deviate in size, or lose the ductility needed. In modern plants, laser sensors are installed along the line to continuously measure the wire diameter, paired with automatic feedback systems that adjust the pulling force in real time. The result is high-strength steel wire coils produced with near-perfect dimensional accuracy and the durability required for cable manufacturing. Reaching the desired dimensions is only half the journey. To truly meet mechanical standards, the steel wire must undergo its next harsh test: heat treatment. At this stage, the wire is fed into a furnace and heated to extremely high temperatures, typically between 1500 and 700 degrees Fahrenheit. Inside the furnace, the atmosphere is tightly controlled in terms of gas composition and heating rate. The heat not only turns the wire a glowing red, but also alters its internal crystal structure, realigning the lattice of metallic grains. This transformation gives the steel the ideal balance between hardness for load-bearing and ductility for twisting without breaking. As soon as the target temperature is reached, the wire is guided out of the furnace and directly into the quenching zone. There, jets of high-pressure air or baths of specialized industrial liquids, such as oil, rapidly cool the steel, effectively locking in the newly formed structure. Right after being heat-treated, the steel wire enters another essential process: anti-corrosion coating. Depending on its intended use, each strand is covered with a protective layer, most commonly zinc galvanizing or a polymer coating. In environments exposed to moisture, seawater, or corrosive chemicals, this layer acts as an invisible shield, preventing the wire from oxidizing over time. Before coating, The wire is thoroughly cleaned with a mild acid solution to remove all traces of dirt, grease, and microscopic rust. It is then either dipped into a molten zinc bath or passed through a polymer coating system where both temperature and pressure are tightly controlled. The coating must be uniform, firmly bonded, and completely free of air pockets, because even the slightest gap can cause the entire wire to deteriorate rapidly when used in the field. Even after receiving its protective armor against rust and seawater, the steel wire is still not ready to serve on the front lines. The inspection stage becomes the final trial, where every flaw, no matter how small, is revealed under the scrutiny of advanced sensors. Nothing can be hidden. The diameter must be accurate down to fractions of a millimeter, and the surface must show no warping or geometric distortion. Tiny deviations, if overlooked, could become the cause of catastrophic failure in the future. Data from each wire is recorded, analyzed, and compared against strict technical standards. At the first sign of irregularity, the wire is immediately removed from the production line. This is more than just a check. It is the ultimate selection process, ensuring that only the strongest and most uniform steel warriors advance to their next performance on the world's grand stage. After passing through all the treatment and inspection stages, the individual steel wires are transferred to the stranding line to be twisted into a complete cable. The stranding system holds dozens, sometimes hundreds of wire spools mounted on massive rotating frames. As the machine operates, these frames rotate rhythmically around a central axis, pulling the wires under tension and twisting them together into a helical pattern that has been precisely pre-designed. Before stranding begins, engineers determine the appropriate core type. The core may be steel, producing an ultra-strong cable capable of withstanding high tensile loads, or synthetic fibers such as polypropylene, which make the cable lighter and more resistant to corrosion in specialized environments. The wires are first grouped into smaller bundles called strands, and then multiple strands are twisted around the core to form the finished cable. Throughout the process, sensors continuously monitor tension, twist angle, and vibration. If any wire is pulled too tightly or left too loose, the system automatically adjusts in real time to maintain uniformity. The stranding speed is also tightly controlled. Moving too fast can deform the wires, while going too slow reduces efficiency. Once the first layer is complete, the machine continues to wind successive layers, compactly aligned according to the set design. Each layer serves a different function. The outer layer resists abrasion, the middle layer bears the main load, and the inner layer stabilizes the structure. Thanks to this distribution, the finished cable is both flexible enough for installation and strong enough to withstand loads of hundreds of tons in real-world use. A finished cable cannot yet be deployed in the field without its final layer, a coating of oil or specialized lubricant. This protective layer is applied either by immersion or by high-pressure spraying, depending on the cable structure and its intended operating conditions.
The pulling speed is synchronized with the high-pressure spray system, ensuring that every section of the cable receives an even coating of lubricant. Flow and temperature sensors precisely regulate the amount of oil used, maintaining consistent viscosity throughout the process. The lubricants are typically mineral or synthetic-based oils, with viscosity strictly controlled to allow them to penetrate deeply into the grooves between the twisted wires. For cables designed to operate in marine environments or under continuous dynamic loads, the oil mixture is enhanced with additives that provide oxidation resistance and protect against electrochemical corrosion. This stage is critical for preserving the cable's mechanical performance. After the stranding process. Quality testing. After the protective lubrication, the cable is still not ready for real-world use until it proves its endurance under the harshest conditions. To guarantee maximum reliability, the final inspection is carried out with large-scale hydraulic tensile machines, cyclic bending rigs, and micro-strain sensors. The cable is pulled continuously until it completely breaks, determining its true load-bearing limit. In other tests, it is twisted and bent repeatedly under varying pressures to simulate severe operating environments. Any sign of irregularity, from microscopic cracks to inconsistencies in structural uniformity, results in immediate rejection. Only the cables that withstand every one of these rigorous tests are cleared to move forward. Once approved, the cable is fed into an industrial coiling system. The winding speed and tension are continuously regulated by a central controller and load sensors, ensuring the wire does not slacken or overlap unevenly. A rotating turntable works in sync with a transverse guide rail, placing each loop of cable precisely into its designated groove. On advanced production lines, cameras and displacement sensors are integrated to detect and correct any deviations in real time. At the end of the process, the cable's ends are secured with hydraulic clamps, and traceability codes, along with batch data, are printed directly onto the coil core. Each finished coil is then mounted on steel or engineered wood pallets, tightly wrapped in heat-shrink film or oilcloth for moisture protection. Automated cranes transfer the pallets into the sealing area, after which forklifts move them to the logistics zone, where they are loaded onto flatbed trucks or specialized containers with anti-roll compartments, ready to leave the factory. Conclusion. From a raw block of metal to a high-strength steel cable, every step stands as proof of precision and technological power. Behind it lies a complex system where even the smallest detail carries critical importance. If you'd like to discover more fascinating manufacturing processes like this, make sure to like the video. Tell us in the comments which stage impressed you the most, and subscribe to the channel so you won't miss our upcoming videos.